a naught d to the power n plus a1 d to the power n minus 1. So fd plus alpha is the same thing where you replace d by d plus alpha. Clear? So this is the property, very important property of the operator function fd, right? F of d acting on this is e power alpha x, f of d plus alpha acting on v. I mean, once I have established this, it will be very easy for you to sit back, scribble and check the truth of the statement. Are you fine today? Arithro, shorita kharab chilo, thik ache? All right, can I wipe this off? Also realize that the rth derivative of e power alpha x is alpha to power r e power alpha x. First derivative would be alpha e power x, second derivative would be alpha squared e power alpha x, third would be alpha cube e power alpha x. So the rth derivative would be alpha to power r e power r alpha x, right? Now once we have bred familiarity with this notation, let's go back to the nth degree equation, linear equation, the nth degree, the nth order linear equation that we started with, okay? All of you understand the algebra of this operators. A naught, where d is d dx, a1 an, all of this is an operator, this is the fd operator acting on y equal to 0, where this is nth derivative with respect to x, this is the n minus 1th derivative with respect to x, and so on and so forth, right? That is fd acting on y equal to 0. We want to solve this differential equation. In real life, when we actually solve differential equations, we have knowledge of the physical implication of the differential equation. We understand the physics or the physicality involved in the differential equation. After all, we don't just conjure up differential equation. We are actually creating a differential equation out of a physical problem. You know, it could be a furnace simulation where we're trying to monitor the flow rates, the heat conduction, the convection, the radiations, etc. And we write the mathematics related to that physics in the form of differential equation. To solve the problem, we actually end up converting that problem into a differential equation and solving the differential equation instead, which would be a solution to the problem that we looked into. So in all situations, the differential equation would have in its back end some physics or something physical. Now, based on our understanding of the physics related to that differential equation, on very many occasions, we start by guessing solutions. And when we guess a solution, then that solution is a trial solution. That's a trial solution. Based on how we build around that trial solution, we solve the differential equation completely. For this differential equation, there is one thing that we realize is that this being a nth order differential equation, its general solution would have n arbitrary constants. Its general solution would have n arbitrary constants. Second, we start with a trial solution to this differential equation. I would not venture too much into digressing why I am taking that as the trial solution, but then there is enough rationale, but then we just fall slightly short of the required mathematics at this level to deliberate on why I start with that trial solution. But then, however, and for whatever reason, I look upon a trial solution of this differential equation as y equal to e power mx. I look upon a trial solution to this differential equation as some y equal to e power mx, let's say. If I can find an m for which, when this operator acts on e power mx, makes it vanish, then I have something to start with as far as the solution is concerned. So in any case, let's say there is a trial solution to this differential equation. Let me say y equal to e power mx is a trial solution. Let's say y is e power mx is a trial solution. Now, this is the original differential equation. So I have like a naught d to the power n plus a1 d to the power n minus 1 plus a2 d to the power n minus 2 plus an e power mx, right? I've started with y equal to e power mx as a trial solution. That means when this operator acts on e power mx, the result must be 0. The result must be 0, right? Now, this operator plus this operator, right? These are also individual operators. This whole thing is a operator function. This whole thing is a operator function. So this could be written as this operator acting on this, plus this operator acting on this, plus this operator acting on this, plus this operator acting on this. All of this must be 0. Now I told you a little while ago, when this operator, the RS derivative operator, acts on e power alpha x, it gives me alpha to power r e power alpha x. It gives me alpha to power r e power alpha to power r e power alpha x. So then when I cause this operator to act on e power mx, it gives me like a naught m to the power n e power mx. When this operator acts on e power mx, it gives me a1 m to the power n minus 1 e power mx plus an e power mx equal to 0. Right? Was very sure. Now I can take since e power mx is not 0, e power mx is not 0 for any finite m, I can then say that a naught m to power n plus a1 m to power n minus 1 plus a2 m to power n minus 2 plus an, that must be 0. What is this? It's a polynomial of degree n in m. It's a polynomial of degree n in m. So in general, how many roots will exist of this polynomial? N roots. So n values of m can be found: m1, m2, m3, mn. So if m1 is a root of this polynomial, then e power m1x must be a solution, because we started with y is e power mx. So if m1 is a root of this polynomial, then one solution to this differential equation would be y is e power m1x. If m2 is another root of this polynomial, then another solution is e power m2x, e power m3x, e power mnx. These are all permissible solutions to the differential equation. Are you all there with me? These are all acceptable solutions to the differential equation. Are you there with me? Now, suppose, so what was this? This was FD. This was FD. What is this polynomial? Realize that this polynomial really can be mentally conjured by replacing the d's by m's. See, a0 d to m to power n, a1 m to power n minus 1, a2 m to power n minus 2, an, right? So in this operator function, if you replace d by m and you solve for m, then e power mx would be the required solution, would be a certain solution of the differential equation. So which means I know FD, this is FD. So what is it that, and I start with a trial solution, y is e power mx. I start with a trial solution, e power mx. How do I obtain m? If I replace the d's by m's here in this operator function, that means fm is a polynomial, would be a polynomial of degree n in m. So fm equal to 0. When I solve this, fm equal to 0, then the solutions are m1, m2, m3, the various values of m, the n values of m that would emerge would be these. These would be the n values of m that would emerge when I solve a polynomial of degree n in m. Which means, if you put m equal to m1, I have a solution y1 which is e power m1x. If you put m equal to m2, I have another solution to the differential equation, e power m2x. If you put m equal to mn, I have yet another solution to the differential equation, e power mnx. Are you there with me? But the point of contention is that none of these solutions is the general solution of the differential equation. None of these solutions is a general solution to the differential equation, because the general solution must spread out n arbitrary constants, and I don't see any arbitrary constant appearing in any one of these solutions. But that's a story for the next part of this discussion. But so far, all that I arrive at is n particular solutions. These are n particular solutions for sure. They are particular, they are not general. All of these would satisfy this differential equation, but none of these is really a general solution to the differential equation. Right? Now let's structure around this. Whatever we have arrived at, let's structure around these. Clear? Now, how are these values of m obtained? When in D you replace d by m, and solve for m, these m's were obtained, m1, m2, m3, mn, and then corresponding to each of these mi's, the corresponding solution yi equal to e power mix was obtained. Now this polynomial of degree n in m this polynomial of degree n in m can have very many combinations of roots, One possibility is that all the, first of all I am assuming that these a0, a1, a2, an are real constants, okay. So one possibility is that all these mi's are real and distinct. That's one possibility, all these mi's are real and distinct. Case 1, all MIs are real and distinct. All the MIs are real and distinct. Now one thing, if y1 is a solution to the differential equation, if y1 is a solution to the differential equation, that means if you put y equal to y1, which is e power m1x, then C1 y1 is also a solution to the differential equation. Because if fd operating on y1 is 0, then fd operating on a constant times y1 will also be 0, because this C1 can come out. So fd operating on y1, that will vanish, right? So if y1 is a solution, C1 y1 is also a solution, where C1 is an arbitrary constant, Similarly, if y2 is a solution, then C2 y2 will also be a solution. In similar, if y3 is a solution, then C3 y3 will also be a solution. If yn is a solution to the differential equation, then Cn yn will also be a solution to the differential equation. Okay. Are you there with me? Which means let me think of a y which is C1 y1 plus C2 y2 plus Cn yn. Let me think of a y which is like a C1 y1 plus C2 y2 plus Cn yn, where C1, C2, C3, Cn are arbitrary constants, where C1 y1 is a solution to this differential equation, C2 y2 is a solution to this differential equation, Cn yn is a solution to this differential equation. Now I claim that this y will also be a solution to this differential equation. How would you know if this y is a solution to this differential equation? If fd operates on y and it vanishes, then this y must be a solution to the differential equation. Clear? So very clearly, when fd operates on y, which is C1 y1 plus C2 y2 plus Cn yn, when fd operates on y, which is C1 y1 plus C2 y2 plus Cn yn, we have like fd operating on C1 y1 plus fd operating on C2 y2 plus fd operating on Cn yn. Hey, but I already established that fd operating on C1 y1 would be 0, fd operating on C2 y2 would be 0, fd operating on Cn yn would be 0. So this whole thing would be 0. Which means if y1, y2, yn were solutions, if y1, y2, y3, yn were solutions, then C1 y1 plus C2 y2 plus Cn yn will also be a solution to the differential equation, where the yi's are like e power mix. How do you obtain the mi's? The mi's are obtained by solving this polynomial of degree n in M. Sounds okay? Now the good thing is, I mean, this is for the case where all the MIs are real and distinct. This is the case where all the MIs are real and distinct. Y equal to C1 y1 plus C2 y2 plus Cn yn. Y equal to C1 y1 plus C2 y2 plus Cn yn would then be a general solution. Why? Because it has n arbitrary constants in it. It has n arbitrary constants in it, right? So n arbitrary constants or general solution. So if mi's were all real and distinct, then the general solution would be c1y1 plus c2y2 plus cn yn, right? Now, for example, if I had a differential equation of the following kind, d squared minus 7d plus 10 acting on y to 0. So then it's essentially, I mean, you can then factorize this. This is fd, this is fd. You may want to factorize this as d minus 5, d minus 7 acting on y equal to 0. D minus 2. Sorry. So sorry, please. It's okay. So this is my FD, this is my FD. The trial solution you start with y is e power mx is the trial solution. And how do you obtain the values of m? By replacing d by m and equating it to 0. So that means m minus 5 into m minus 2 equal to 0. So m would be 2, 5 distinct values of m. So then the general solution would be y would be c1 e power m1x 2x plus c2 e power 5x. This would be the general solution to this differential equation. This would be the general solution to this differential equation, right? Suppose we had FD, which you realize the FDs, you are at liberty to factorize the FDs, right? Suppose the FD turns out to be d minus 1 into d plus 4 into d minus 2 into d plus 6. Suppose this was FD, right? And we have a differential equation FD acting on, and this would be a differential equation of order 1, 2, 3, 4, because d to power 4 highest order derivative would be 4, right? So FD operating on y equal to 0, right? Now the solution would be obtained by replacing d by m, fm equal to 0. Fm equal to 0 would give me like a m minus 1 into m plus 4 into m minus 2 into m plus 6 equal to 0. So the values of m are 1, minus 4, 2 and minus 6. So the general solution to the differential equation would be y equal to c1 e power x, c2 e power minus 4x, c3 e power 2x, c4 e power minus 6x. These are the various values of m. This is the general solution. Dig order 4 arbitrary constants. E power x, e power minus 4x, e power 2x, e power minus 6x. These are particular solutions, but this scheme is the general solution scheme of the differential equation, right? Now suppose I had the following. This was the case where all roots were distinct and real. This was the case where all roots were distinct and real. But suppose two of the roots were coincident. Suppose two of the roots were coincident. So we had d minus alpha 1 whole square alpha 2 acting on y. This was a differential equation. This was a differential equation. So in this case, do you realize that m1 would be equal to m2 will be alpha 1? Two of the roots are coincident here, right? How do you obtain these mi's? By replacing d by m and equating it to 0. Then you obtain the values of m, right? In this case, this is d minus alpha 1 into d minus alpha 1. Two factors, so two of the roots become equal to alpha 1, and then let's say m3 is alpha 2 and so on and so forth. Mn is alpha n minus 1. Okay. Now if you attempt to write the solution to this differential equation, now you attempt to write the general solution to this differential equation when, let's say, two of the roots are coincident. When two of the roots are coincident, suppose you want to write c1 e power m1x, that means e power alpha 1x, plus c2 e power alpha 1x, right? c2 e power alpha 1x plus c3 e power alpha 2x plus cn e power alpha n minus 1x. Now I claim that this is not a general solution, because after all, these two if I combine, then I have like c1 plus c2 would be one arbitrary constant c. So c e power alpha 1x, c e power alpha 1x plus c3 e power alpha 2x and so on and so forth. Do you realize that the number of arbitrary constants is no longer n but n minus 1? So this is not a general solution if two roots coincide. If two roots coincide, this is not a general solution. What now? Again, without proof. Again, it's not difficult to prove that, but we'll keep ourselves away from the proof of this result for the time being. Suppose, see, in the general solution, the contribution made by this is some constant into e power alpha 2x. The contribution made by this factor is some arbitrary constant e power alpha 3x. Contribution made is some arbitrary constant e power alpha n minus 1x. Now these two factors, when they are identical, d minus alpha 1, d minus alpha 2, alpha 1, then let me tell you that the contribution that this would make to the general solution, without again rendering a proof for this, the contribution made by this to the general solution would be c1 e power alpha 1x plus c2 x e power alpha 1x. One of the factors would contribute e power alpha 1x to the general solution. The other factor, which is the same, is like x e power alpha 1x would contribute like a x e power alpha 1x. And then we have like something into e power alpha 2x plus something into e power alpha n minus 1x. This would be the general solution. This would be the general solution, which could be written as c1 plus c2x. Now c1 plus c2x is not a constant. c1 plus c2x e power alpha 1x plus something into e power alpha 2x plus something into e power alpha 3x plus an arbitrary constant e power alpha n minus 1x. So if two roots are coincident, then those two coincident roots contribute to the general solution. See, if alpha 1 are the two coincident roots of this fm equal to 0, then the contribution made to the general solution would be e power alpha 1x into c1 plus c2x. Suppose if I had